This lecture is going to cover different algorithms for pairwise sequence alignments. What's needed to define an optimal pairwise alignment? First, you need a scoring function. That is a function that gives you the score of how well any letter X matches a letter Y. There are many different types of scoring functions. For the sake of the lecture, we'll define one that takes a score P if X and Y are the same letter. If any of the letters are gap, then it will take a gap penalty instead. And if it's not the same letter and not a gap, then it will take a mismatch score M. You also need an alignment approach. If you're interested in aligning the full-length sequences to each other and get the most optimal alignment from the full-length sequences, then you are searching a global alignment. If you instead just want to find the highest scoring stretch of an alignment, then you are looking for a local alignment approach. Or you, if there's sort of a crossbreed between the two in a semi-global alignment, where you try to align the core of these sequences as best as possible. But if any of these two sequences are spilling over, you are not counting the extra termini of a sequence. So all these three are valuable options. Both differences in scoring function and in the alignment approach will render very different alignments. So these choices have direct implication on the alignment quality. And the alignment approach will itself will govern which algorithm we use to sequence or to align sequences, whether the scoring function mostly differs the appearance of the alignment. The most famous algorithm for matching two sequences is known as the Needleman-Wunsch algorithm. It stems from the 70s, and it is the first one to introduce so-called dynamic programming to the problem. That is, that we, instead of trying to put up a function in closed form, we instead define the problem as a recursion. And in this case, it's a recursion that will formulate what we know as a dynamic programming matrix. So it's a matrix that we here denote S with the size of n plus 1 and m plus 1. So where n is the length of one of the sequences, m is the length of the other sequences. We subsequently fill or we initiate the problem by filling the borders of the matrix with gap penalties. So you will, in the position 0, 0, you will fill it with 0, and then you will add one gap penalty per row or column you progress to the sides with. This is rather straightforward. I will show you an example later on. What's probably a little bit harder to get is the subsequent part where we define the problem as a recursion. And this is where we say that each element S of Sij is a function of the previous positions in the matrix. So you have firstly one probability of going diagonally in this matrix. This is sort of the event where you have a match or mismatch between the sequences. And this will now give you, you will just add the score of the previous position to the probability of the match or mismatch. So this is Si1 minus 1 and J minus 1 plus DAB. There as well is the probability that there's a gap in the second sequence. And in such case, we just need to move upwards to the Si minus 1 and the J position. And as well, you could do the same thing with if there's a gap in the second sequence. So all these three options that are, you just select whatever path that gives you the best score or the maximal score. So this is a sort of a definition going from the fact that you have one element already calculated, and you can then subsequently calculate for the other ones. So this is sort of for each element you will look for its predecessors and see what value do they have, and then you make an addition to that position. The final score of the alignment will be now given by the bottom right element of the matrix, the SNM, and you can subsequently as well find the optimal alignment by backtracing for this. Okay, so maybe an example will come nicely here. Say that we want to align two sequences, GAC and the sequence ACG. We want to use a global alignment strategy, and we want to use a distance matrix a distance score that comes from either scoring 1 if the X and Y are equal, and otherwise you get the -1. So both for mismatches and for gaps, we will give the sequence a score of -1. Okay, so first off, we just fill in the borders of this matrix. We set a 0 of this element 0, 0, and then we just add gap penalties to the first row and the first column, just as the initiation condition was saying. Okay, so subsequently we move to the first element, the S11, and the way we can calculate this is by now looking at position S00, which has a score of 0, and we add the match or the scoring function of G to A. So from the sequence A we take the first position, and from the sequence B we take the first position, and that score would be -1. So the score of 0 plus -1 is -1. Similarly, we can look on positions S01 and add a gap penalty to that. So that's -1 plus -1, that's -2. Similarly, we can look on the position S10 and add a gap penalty to that, and that's -1 plus -1, which equals -2. Now, the maximal element of these three different options would be -1. So we write a -1. Now you might wonder, what's the significance of the red arrows I draw here? The red arrows are there to keep you back pointers to the path that leaded up to a certain score in a certain element. The real significance of this will become clearer towards the end of the alignment, where we try to, when we after have finishing the sequence alignment, wanted to use the actual alignment that this gives rise to. Okay, next position. So we want to calculate S12. Again, we can use this recursive formula. So we look on S01, which is -1, and add a mismatch probability to that. That's -1. That ends up being -2. We can as well look on the different mismatch or the different gap penalties together with the other two positions. So that's in this case -2 and -1. So we end up with our three different paths going -2, -3, -2. This leaves us in a position where we could have come to -2 from two different paths. So we draw red arrows for both these positions, for both these options, and we assign the element a -2. So last element in the same row, S13. Let's take the element S02 and add a match probability, in this case, between G and G. That's -2 plus 1, which equals to -1. We as well have the possibility to move to this position from above. So it's S03 plus a miss or a gap penalty. So that's -3 plus -1. That's actually -4. We can as well use S12 from the element, move from S12 earlier on the same row, which scores -2, and add a gap penalty to that. That's -3. So out of those three elements, we select the maximal element, and that's -1. So the score of the alignment coming to this position is -1. Next step, we move down to one row, and we select the first element or the first position in the second row then. So S21, and that could either be reached by a diagonal traversal where we match A and A. That will give you the A versus A will score +1, and if you add that to the score -1, you will get a 0. Similarly, you can use the score of S11 and add a gap penalty to that. That will render a -2. Or you move horizontally from S20, which would, and add a gap penalty to that. That would be -2 plus -1, and that renders a -3. So the diagonal path was the maximal path in this case, and we record a score of 0 for S21. Okay, S22 then. How do I get that? Again, we use the same formula, so we either move diagonally from S11 with a mismatch probability, that will give you a -2, or you move vertically from -2 to and add the gap penalty to that renders a -3 in the end. Or you move horizontally from 0 and add a gap penalty to that renders -1. So it turns out that the horizontal movement is the preferred one, so you set the -1. And the last element of the second row, S23, that could be now calculated either by a mismatch probability, diagonal mismatch probability, giving you -3, a vertical movement to -2, and or a horizontal movement which gives you -2. In this case, both the horizontal and vertical movement would give you -2, and we give you set the the score to -2. Let's now jump down to the last row. The element 3, 1 could be reached either diagonally from 2, 0 with a mismatch. That's -2 plus -1 equals to -3. Or we move in vertically with a gap penalty from S to 1. That's it's a total of -1. Or we move horizontally from -3 with a gap penalty equals to -4. So hence we take the vertical movement that renders -1. S32 could either be reached diagonally from a 0 with a match between C and C, and that will give you a score of +1. Finally, a positive element here. Or you could move vertically with or horizontally, in both cases, a -1 plus a gap penalty with a -2. This gives you the element, the maximal element being +1 with a diagonal moment. And S33, finally we reach to the end of the matrix. S33, that's defined now by either moving diagonally from a -1 with a mismatch, and that gives you a -2, or you move there vertically from -2 with a gap penalty, that's -3, or you move there horizontally from +1 with a gap penalty, that's 0. So horizontally it is. So the final element, S33, will be set to 0. Now we've completed the full dynamic programming matrix. What can we use this for? Well, first off, we can tell the score of the alignment. It's 0. Since the element of S33 is 0, the score is 0. But we can as well use so-called backtracing to find how we ended up in the position 3-3. So it's just to follow the arrows backwards now. So now we have use of these red arrows that we draw. And these will now be in turn reached by a gap with a G, a C matching a C, and an A matching an A, and a G matching a gap. If we now sort of just put that in reversed order, we see the final alignment as GIC with a gap and the gap ACG. Sometimes in these examples you will note that there are multiple different paths that will be equally that will be able to end up with the same score. That's actually an actual reflection of the fact that there are multiple different alignments that might have the same score. In this case, however, there was a unique solution to the problem. If we instead of a global alignment want the local alignment, there's an alternative algorithm to use, and that's known as the Smith-Waterman algorithm. It's very similar to the Needleman-Wunsch. However, there are some notable differences. The first difference sits in the initiation of the algorithm on the dynamic programming matrix. Because instead of using gap penalties here, we set all elements, the first row and column, to 0. Another difference is that we as well introduce yet another possibility for the alignment. We always compare the alignment score of the previous elements to 0. So if the three options to move don't render a higher score than 0, then we instead start to reset the alignment and start from 0 again. And instead of looking for the bottommost right position for scoring the alignment, we instead just select the maximal element wherever that might appear in the dynamic programming matrix SYJ. So if we use this for the same example as we were using previously, we see that we, well, the initiation again, it's instead, it looks a little bit different, but we would get zeros instead of a set of gap penalties. We can as well start to fill this in, and I will not walk through all the details of this and leave that for an exercise for you. However, I will just sort of stay on the calculation of the last element here. In this case, we are wanting to calculate S33, and there are 4 different ways to reach this position. So we either come here to the position diagonally, and that's from a 0, so with a mismatch, and that's a 0 plus -1, so that renders a -1. We move there vertically, and that's a 0 plus a gap penalty, that's -1. Or we move there horizontally, and that's a 2 plus a gap penalty, and that's 1. We have the 4th option as well with a 0. So out of all these elements, the largest element is the one moving in horizontally with a 1. Hence we select the 1. When we want to score the Needleman-Wunsch, or when we want to score a Smith-Waterman alignment, we are using backtracing again, but now this time we're doing so from a position, the maximal element anywhere. The maximal element in this case is for S32, which happens to be 2. And then we backtrace that to the first point where we don't have any point out from, and that's now to S10. And the backtracing from this gives us now an CC with an AA. So the final alignment here is just the 2 positions AC for both sequences, and we are cutting away the termini. We also have the possibility to calculate semi-global alignments. It's the algorithm is sort of a it's looking similar. The initiation is the same as for the Smith-Waterman. However, the recursion is the same as for Needleman-Wunsch. And the final score is calculated as the maximal element on the rightmost column or the bottommost row, and do backtracing from that to whatever position you end up in. I will not use any examples of this here in the lecture. So thank you.